Right, there are a wide range of statistical functions, and they differ largely in terms of how many parameters they have. So how simple or how complex they are. The exponential is the simplest, a single parameter model. There are various 2-parameter models. Log logistic was one of them, the one we just looked at. There's 3-parameter models, there's 4. Indeed, I haven't done it, but you can have a 5-parameter model. These are examples taking the generalized gamma of different hazard functions. Remember what the hazard is showing. If a patient survives 6 months, 9 months, a year, if they make it to that point, what is their risk at that point of then dying? Now, if you think about it, for different interventions, you might expect the hazard to decrease and then maybe over time start increasing. Or maybe the hazard starts increases to start with as a consequence of the intervention before decreasing. Indeed, sometimes the hazard may just be constant. And so, depending on the particular intervention and the condition we're looking at, different shapes of hazard function will be appropriate. It's a U shape here where the risk of death is really quite high to start with, but if you survive the first few weeks, then the risk falls quite dramatically, and then it might begin to increase slowly over time, or it might go up more rapidly over time. These are all potential shapes. There is, in fact, it's not shown here, there's one called the bathtub. And if you think of a bathtub, it's going to be a very steep decline to start with, and then more or less constant, and then increasing rapidly at the end. And so for some conditions, that makes the most sense. And so I guess what this is highlighting is, in thinking about the distribution to use, you have to think a bit about the underlying condition and what happens to patients. So again, I'm emphasizing it's more than just a statistical exercise. You've got to get the statistics, as it were, to marry up with the clinical information. Right, I'm going to give you one example in a little bit more detail. But as I say, this is not about teaching lots of different, it's not about teaching statistics, but just to give you a flavour of it. This is a very popular distribution. I'm not quite sure why it's so popular. Maybe because it's flexible. It's fairly flexible. And it's called the Weibull distribution. So formally, it's a survival function. Survival is a function of time, and it's specified as the exponential of minus lambda times t to the alpha. So it's, as you can see, we've got 2 parameters, lambda and alpha. So Weibull was here, one of the 2-parameter models. Okay. So the hazard function with the Weibull can be increasing or decreasing with time, depending on this parameter alpha. If alpha is greater than 1, the hazard rate increases with time. In other words, the proportion of the group who are dying is rising in succeeding time periods. If alpha is less than 1, the hazard rate is decreasing with time. And if alpha equals 1, the Weibull becomes an exponential model. It's a constant hazard ratio. So it's very flexible, but notice in this model, the hazard can't change direction. It's either increasing, constant, or decreasing. It can't change direction. So here we are, here's some examples. So here's the constant one, And for some purposes, that's a very good model, constant hazard, at least for the relevant time period. On the other hand, if the patients are quite long-lived, it's quite likely that hazard at some point is going to start increasing, just because older people are more exposed to other comorbidities. So we've got these possibilities. This is a decreasing, and then we've got a couple of increasing ones here. So yeah, the reason it's popular is it's quite simple to estimate and it's flexible. Right, now the examples we've had so far, particularly his cytidine example, it assumed that a particular survival function was appropriate and it fitted it to the entire period of the data. An alternative approach that's sometimes used is what's called piecewise survival curves. Now the idea here is that what happens to the patients isn't a sort of steady process, but maybe there's different phases to the condition. So rather than fit a single curve to the data points, you might fit two or more curves or pieces of curves. So one example here was cabazitaxel, which is treatment, I think it's prostate cancer, metastatic prostate cancer, if I recall correctly. And what they found was that in the data, early on, there were quite a few deaths in the trial from cabazitaxel-induced neutropenia. And then if you survived that first phase of treatment, these deaths ceased. And so the next piece of the survival curve was a different shape from the first piece. The first piece was quite high hazard rate, but it was short-lived. Then the second piece was people dying at a much lower rate. And so rather than fitting a single curve, the manufacturers in this case said, in that first phase, we'll just use the Kaplan-Meier observations, and that'll be our survival curve. But then, in the second phase, we're going to use a Weibull function. So that's a piecewise. And the underlying idea here is that the final piece may be the best predictor of what happens next. And it's got some strong intuition that if some patients are dying very early on, they're not very helpful in predicting what happens to the survivors. Much more useful is the second piece of the survival curve. All the early deaths have disappeared, and we've got a much steadier progress, and using that part of the curve to extrapolate or predict the future.